Okay, so today we're going to look at average and instantaneous rates with graphs. So we can use a graph to figure out the average rate, which is just the slope of 2 points in a graph, and or the instantaneous rate, which is the slope at a specific instant in time. With average rates, we are just looking at the slope between 2 points. So again, if we're talking about this graph, you can see that the slope at the start is pretty steep at that first point, and it's a little shallower at this point, but it's changing over time. So the average of those slopes will be this red line, the slope between these 2 points. That's your average rate between those 2 points. It's not going exactly that speed all the time, it's the average of that. And again, how we find that is just finding the slope of that line, which is your rise, which is our change in concentration, and our run, which is our change in time. Now, to find the instantaneous rate at a specific time, we got to find the slope of something called a tangent line. And a tangent line is a straight line through a specific point on the curve. We use this method because the rate of reaction changes over time, and you can't find the slope of a single point. To find slope, you actually need 2 points to find out how steep they are. What we can do is we draw a line that's tangent to the curve. In other words, it only hits the point at that instant where you see the point on the graph, and that is approximating the slope at that instant in time. Now, if you continue on in chemistry and math, you'll be able to use calculus to find the actual equation of the tangent line and hence its slope. But for us in this course, because we're not doing calculus, we're just going to draw our tangent lines. So first things first, a little bit of review. So I've given you some data. We're doing the change in concentration of SO2Cl2 over time. So we're going to find the average rate at the beginning of the reaction and towards the end of the reaction. We're going to find out why those rates might be different, or we're going to talk about why those rates might be different, and then we'll do tangent lines right after. So in the first 200 seconds, here is our time interval. So from here to here. So remember that our rate is just going to be the change in SO2Cl2 over the change in time. So our change is going to be 0.067 moles per liter, take away 0.1 moles per liter over that time interval, which is 200 seconds. That's the change in time. So my answer ends up being 1.65 times 10 to the negative 4 moles per liter times seconds. Now, your answer will be negative because the value is dropping, but remember, we always state our rates as a positive value. Now, if we're talking about the average rate for the 500 to 700 time interval, we're going to go same thing. It's going to be the change in concentration over change in time. So our change in concentration is 0.025 from 0.037, and again, 200-second time interval. So our change in concentration over time, or our average rate over those 200 seconds, is 6 times 10 to the negative 5 moles per liter times seconds. And again, it should be negative, but we're making it positive. Now, it says account for the difference between the rates in A and B. So if we're looking at these two rates, you should notice that this one is significantly lower or slower. Now, why would it be slower towards the end of the reaction compared to the beginning of the reaction? And I want to go back to collision theory. So if we're talking about collision theory, at the start of the reaction, that's when you have the majority of your reactants, the most reactants you'll ever have in a reaction. So that's when you're going to have the majority or the most collisions, most successful collisions as well, which is what causes a faster rate at the beginning. And as the reaction proceeds, the amount of your reactants is going to be dropping. So you're going to get less and less collisions over time. So B is slower because you have less reactants and less collisions. And when we graph a reaction rate, what you'll see is you should see a curve like this. Now, this is not a very steep curve, but you can see a curve nonetheless. The slope at the start of the graph is steeper than the slope at the beginning or at the end of the graph. And that's because over time you're using up reactants, you're making products, so your rate is slowing down. So now the next question is we want to find the rate at 400 seconds. So here's my point at 400 seconds. And in order to do that, we're going to draw a tangent line. Now, it's not going to show up great on my screen because The pen might not exactly hit the point and all this kind of thing. So I'm going to do the best I can on my screen, but you can use a straight edge on your paper and draw a tangent line. Now, again, the tangent line should only hit that point right there on that graph. So we just want to try to level our ruler against the graph as best as we can and try to draw a line, I might have to back this up a bit, that only hits that point. And if you imagine the graph was like a balance, that line should almost be balancing on that point. So that's a decent tangent line. Now, once you've drawn your tangent line, we're going to try to find the slope of it. So we got to find the rise and the run. Now, in order to do that, we need 2 points. Well, I'm going to use this point because we know that point is on the line for sure, and we actually know those values directly from our data table. So if I look at the 400 time mark on our data table, this is your x value is 400 seconds, and your y value is 0.045 moles per liter. Now, to find another point on the line, you could choose any point you want, as long as it's on that line. I want to try to find a point that's easy for me to read on the graph. So I'm going to look for a point that will intersect, like if I'm looking, let's say here, I want to pick a point that intersects in the corner of a grid space, if that makes sense, rather than like, I wouldn't pick a point that's kind of in the middle, because then I got to estimate how far across it is. So I'm going to look down my line, and I'm going to find a point that hits kind of the corner of a box. And I see a few. It doesn't really matter which one. I'm going to pick this one because it's right on 600. Now, your graph and your line might be different, and your slope of your tangent line is going to be different because we're just drawing these by hand. And again, that's where calculus would come in. So if I look at this point right here, this is at 600 seconds. So 600 seconds. Now, for me, that's easy because I actually know the value at 600 seconds is 0.03. According to, this is not making sense. According to the data, or according to the graph, it's actually not going to be 0.03, it's going to be 0.025. If I look on that scale. There it is. So now I'm going to find the rise and the run. So here's my rise, and here's my run. Now remember, your rise is just your change in concentration, and your run is now your change in time. So my slope for this section of the graph, I have to write it down here. Slope is going to be the change in concentration over the change in time. So my change in concentration, I started at 0.045 and I ended at 0.025. So 0.025 moles per liter, take away 0.045 moles per liter, over my change in time from 400 to 600. So it ends up 600, take away 400 seconds. So when I solve that out, I got 0.025, take away 0.045, divided by the change in time, which is 200 seconds. So I got 1 times 10 to the negative 4, and that would be moles per liter times seconds. So that's basically how you would solve for your slope of your tangent line. Now again, with my graph, it's not perfect because I'm trying to do this on the computer screen. You'll have a better time probably getting a better tangent line to the graph in your notes, but you should get a value somewhere in the ballpark of what I got. It could be quite a bit different even just because of rounding and stuff like that, but at the end of the day, that's how we would solve it. So your assignment, as you calculating a bunch of average rates, and then you're going to graph the data, and you're going to draw 3 tangent lines on your graph. If you use different types of graphing software, graphical analysis will allow you to actually just do tangent lines right on the computer screen, and you can find the slope right there. Drawing them by hand is not always the best, but I really want to stress that average rates are between 2 points, instantaneous rates are at an instant in time.